Right now, you are holding one of the strangest objects human beings have ever built. Ask it to multiply two enormous numbers, and the answer appears before your finger has left the glass. But here is the part almost nobody stops to think about. Your phone does not know what a number is. It has no digits, no symbols, no tiny mathematician hiding inside. All it has is switches, billions and billions of switches. And every piece of mathematics a computer has ever done, every rocket launch, every bank balance, every pixel of this video, comes down to one question. Is the switch on or off? So let's start small, smaller than small. Picture one light switch on a wall. It can tell you almost nothing. It has exactly two states, on or off, 1 or 0. Engineers call this a bit, and 1 bit is pathetic. It can count from 0 all the way up to 1. But add a second switch and something interesting happens. Off, 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 on off, on. Suddenly you have 4 combinations. 3 switches give you 8, 10 switches give you just over 1,000, and 64 switches can give a private serial number to every grain of sand on every beach on Earth. This is binary, counting with 2 symbols instead of 10. And you already count this way. When you pass 9, you run out of digits, so you write a 1 and carry it into a fresh column. 10. Binary does the same thing. It just runs out of digits sooner. 0, 1, carry. Now for the strange part of the story. The mathematics inside your phone was invented before the light bulb by a man who never saw a computer and never would. England, 1854. George Boole, a shoemaker's son who taught himself mathematics from library books because his family could not afford to keep him in school. Boole had an obsession that his colleagues found slightly embarrassing. He believed human reasoning itself, logic, thought, argument, could be written down as algebra. Not algebra about numbers, algebra about truth. In Boole's system, there are only 2 values, true and false, and just 3 basic operations, and, or, not. True and true makes true. True and false makes false. Not true makes false. That is the entire toolkit. The world mostly shrugged. Boole died of a fever in 1864, and his algebra of thought sat on library shelves for the next 70 years, admired and almost completely useless. Then, in 1937, a 21-year-old graduate student at MIT found himself babysitting a monster. His name was Claude Shannon. The monster was the differential analyzer, a room-sized mechanical calculator of spinning shafts and gears, and part of Shannon's job was tending the electrical relays that controlled it. A relay is just a switch, but a special kind. A switch flipped not by a finger, but by electricity itself, which means one switch can flip another switch. And staring at those clicking relays, Shannon saw something nobody had seen before. Wire 2 switches in a row, and current gets through only if the first and the second are closed. That is Boole's AND, built out of metal. Wire 2 switches side by side, and current gets through if either one is closed. That is Boole's OR. Boole's forgotten algebra of thought was not philosophy, it was a wiring diagram. Shannon wrote it all down in his master's thesis. People have called it the most important master's thesis of the 20th century because it proved something astonishing. Anything you can express in logic, you can build. Today, nobody uses clicking relays. We use transistors, switches with no moving parts at all, flipped by a whisper of voltage. A single transistor is so small that thousands of them fit side by side in the width of one human hair. Wire a few transistors together, and you get what engineers call a logic gate, a tiny circuit that answers one yes or no question. An AND gate turns on only if both of its inputs are on. An OR gate if at least one is. A NOT gate flips whatever you give it. Simple, almost insultingly simple. And this is where the magic starts. Because there is one more gate to meet, the exclusive OR, XOR. It turns on when its 2 inputs are different and stays quiet when they match. Now watch closely what that means for 2 bits. 0 and 0 give 0. 1 and 0 give 1. But 1 and 1 give 0. 0, 1, 1, 0. That is exactly, precisely, the last digit of binary addition. And the AND gate? It fires only when both inputs are 1, which is exactly the moment addition needs to carry a 1 to the next column. So put one XOR gate and one AND gate side by side. Feed them the same 2 bits, and you have just built a machine that adds. Engineers call it a half adder. It does not know it is adding. Nothing inside it knows anything. Electricity is simply flowing downhill through metal. And yet the answer comes out right every single time. To add numbers bigger than 1, you chain adders together, one for each binary column, each one passing its carry to the next, like a bucket brigade. Chain 32 of them, and you can add numbers in the billions. 64, and you are into the quintillions. That chain sits at the heart of a circuit called the arithmetic logic unit, the ALU. Every processor has one. It is the room where the math actually happens. But hold on, addition is one trick. What about subtraction? Here, the engineers got sneaky. They invented a way of writing negative numbers called 2's complement, where subtracting a number becomes identical to adding its negative twin. Flip every bit, add 1, and the very same adder circuit now does subtraction. No new hardware, just a clever disguise. Multiplication? Mostly repeated addition, with the digits shifted along. The same trick you learned doing long multiplication in school. Division? Repeated subtraction. So follow any computation down far enough, a spreadsheet, a video game, a weather forecast, and you hit the same bedrock. Adders. It is adders all the way down. Which brings us to the part that is genuinely hard to hold in your head. The speed. Inside your processor, a sliver of vibrating quartz keeps time, and that clock ticks billions of times every second. On every single tick, the adders swallow fresh numbers and push out answers. 3 billion ticks a second, from a chip the size of your fingernail. A modern phone processor packs in somewhere around 20 billion transistors. That is more than 2 switches for every human being alive. If every one of those transistors were a person flipping a light switch on cue, your phone would be a civilization, larger than Earth's, working in perfect coordination so that you can watch a cat fall off a sofa. Now, you might object. Computers clearly do more than whole numbers. What about decimals, curves, physics? Decimals travel in a format called floating point, essentially scientific notation written in binary. Some bits store the digits, a few more store where the point should float. And everything else your computer does is just numbers wearing costumes. This voice you are hearing? Numbers. The colors on your screen? Numbers. Your photos, your messages, your location? Numbers, numbers, numbers. Which means everything a computer has ever done for anyone was, underneath it all, arithmetic. Oceans of arithmetic, one bit at a time. So, how does a computer do mathematics? The honest answer is, it doesn't. Not the way you do. No switch understands 7. No gate knows it is carrying a 1. Ask a transistor what it is doing, and the truthful answer is getting slightly warm. The understanding lives somewhere else, in the arrangement. In Boole's algebra and Shannon's wiring, frozen into silicon by thousands of engineers you will never meet. And maybe that should sound familiar. Inside your skull are roughly 86 billion neurons. Not one of them knows what 7 is either. Yet here you are, understanding. Mindless parts, arranged with enough care, begin to look very much like a mind. On, off, 1, 0. Everything else, everything, is just very, very good arrangement.